Let's put everything together that we've learned about rational functions and identifying key features so that we can use them to graph. I've sketched the parent function for rational functions, and you should go through the steps to identify the key features for this because it will, I think it will be really illuminating about going through here and what the steps and how they look different, what the steps are and how they look different for the parent function. The whole goal is to make the graph look as close to the parent function as possible. So we're going to do that by getting these functions into reduced form and then identifying key features from there. So let's look at problems number 1 and 2. I'm going to do problem number 1 in blue. And the first thing I see is that I need to factor my quadratic pieces. And so factoring means getting them into the parts that multiply. I've got 2 times x. That's the only thing that will make my numerator. And then I've got x plus 2 and x minus 2. And I know that from the difference of squares rule. So then we look at key features now that we can't go any farther. And the first thing I notice is that the domain are all the values of x that x can't be equal to because the denominator can't be equal to 0. So the domain is when x can't be equal to negative 2 or positive 2, because that's what would make the denominator 0. Domain means denominator can't be 0. So then we look at what's going on with the factors. And when we factored, I noticed that we didn't cross anything out. And if we didn't cross anything out, then we have no holes. There are no holes in our graph. So there's no holes because we didn't cross anything out. Now the holes were related to the vertical asymptotes. So if we didn't cross out the holes, then, there was nothing that we crossed out. So we had no holes, but we didn't cross out other factors in the denominator, and that's where we find our vertical asymptotes, is those factors in the denominator that we didn't cancel out. So our vertical asymptotes, there are 2 of them because there are 2 factors in the denominator that didn't get crossed out, and those are at x equals negative 2 and positive 2. And then if there are vertical asymptotes, there might be horizontal asymptotes, especially if we're looking at rational functions. And the vertical asymptotes have to do with the degree. The degree of the function is that highest exponent, and that highest exponent in reduced and in the given equation, those degrees are equal. So these degrees in the equation are equal. And that means that if they're equal, then the horizontal asymptote, that horizontal line is the ratio of the leading coefficients, and that reduces to 2. Now, we want to graph with a point. How do we know where to start with some of this if we don't have a point? So let's find a point. And the easiest point to find is when something equals 0. Everything's in terms of x. So let's find the x-intercept when x equals 0. So that means it's 2 times 0 over 0 plus 2 and 0 minus 2. And it doesn't matter what the denominator equals in this scenario because that numerator makes everything equal 0. So our x-intercept's actually at the origin, and now we can graph all of our pieces. So let's graph our pieces, starting with the holes, right? There are no holes, and then we've got the asymptotes. So let's do the asymptote, the vertical asymptotes in this galaxy pin vertical asymptotes. I can make that a little bit bigger. Vertical asymptotes at x equals -2 and +2. And then we've got a horizontal asymptote at y equals +2, horizontal across. And the last piece that we found was the x-intercept, and that's at the origin, this x-intercept. And now we've got some things we can graph with. We want it to look as much like the rational parent function as possible, starting in the first quadrant. So if we're bounded by those asymptotes, I'm going to do this in rainbow pen. So if we're bounded by the asymptotes and we have to start in the first quadrant, first, second, third quadrant, then we have to start here, and that's the first L shape we'll make. And we're bounded by the other quadrant in the middle. We can't just leave it blank, but it has to be opposite from the one that we started with. So we've got this parabolic section in the middle. And then to satisfy the asymptotes on the last quadrant as we move across the coordinate plane, then we've got to make it opposite from this other piece that we drew, and that's where we get this L-shaped figure here. So we do the same thing for number 2, right? We would get everything into reduced form by factoring. So we've got x minus 4 over x plus 3 all over x plus 3 times x minus 3, those difference of squares. And then now we've got some stuff that crosses out along with stuff that doesn't. The domain are all of the values of x where the denominator can't be 0, so it's bounded by that. So the domain is everywhere where x isn't equal to negative or +3. And then we see that stuff did cancel out. So if it did cancel out, there's a hole there. I can remove it, and the holes are removable. So there's a hole at x equals -3. And when we substitute that back into our function, we get y equals -7 over -6, which is +7 over +6. And that's a point on our graph that we will graph. And then we had some stuff that did cancel out, that did reduce. So that vertical asymptote is at x equals 3. And then if our degrees were equal, then our horizontal asymptote is at the leading coefficients ratio at 1. So now we can graph everything. We've got our vertical asymptote at 3, our horizontal asymptote at 1. We've got our hole here at -3 and 7 over 6. And now we graph everything as close to the parent function as we possibly can. Now we have to start in a different part. We have to start in this different part over here for this function. And I'm going to leave it to you to figure out why. So we have these 2 models, and you have the rest of these practice problems, and you'll identify these key features and then graph them on the coordinate planes provided.